In this video, we will be looking at section 6.1 and 6.2. So, what this chapter focuses on is when we talk about continuous random variables. And we're going to talk about normal distributions, but on our way there we will talk about uniform distributions. And what happens with a normal distribution is that it is bell-shaped and symmetric. And there is a mathematical formula for this curve, but what I want you to notice is the peak of our curve is at the mean of the distribution, and the spread is defined by the standard deviation. Now, here is the formula, and do not worry about that at all. We will never, ever, ever use this formula. But the point is, we will be using the curve that it defines for the rest of the course. So, it's a mathematically defined curve that's symmetric with the mean of mu, and then the width of the curve is defined by the standard deviation, which you can see in this formula. Now let's talk about how we're going to use this. So we know that we're going to talk about the standard normal distribution, and I think we've talked about it briefly before. You know that it's a bell-shaped curve. You know that its mean is equal to 0 and its standard deviation is equal to 1. So what we're going to do is we are going to develop the skills so that we can use this curve to help us find probabilities. Now, to do that, we need to find z-scores, and we will look at the area under the graph. Now, the first thing we're going to talk about is we're going to talk about a continuous random variable, and that has a uniform distribution. That means its values are spread evenly over the range of probabilities. The graph of this type of distribution is a rectangle, so it's very easy to find the area of a rectangle. We know the area of the rectangle is length times width, or length times height. What are some examples of uniform distributions? In your book, in example 1, they talk about the wait times for the subway train, and they say that train leaves Times Square every 5 minutes, and so the waiting times for passengers is distributed by a uniform distribution between the times of 0 and 5. Okay, that's the dimension of our distribution. The thing about a probability distribution is the area under the curve is always 1. And so if our width is 5, then our height will be 1/5, because we know the width times the height is the area, and the area of a probability distribution is always 1. And we call this a density curve. And the density curve must satisfy the properties that the area is always 1, and every point on the curve is above the x-axis. So in other words, we can't have any negative vertical heights. And because the total area under the curve is equal to 1, there's a direct correspondence between area under the curve and the probability, because the probability of all possible events is always equal to 1. For example, if a satellite crashes at random on the Earth, what's the probability that it will crash on land? Well, we have to do some research here. So we need to look at the map. Now, this happens to be a Peters projection, which may look a little bit different than the flat maps you're used to seeing. What this does is this talks about true land area. So you can do a little research on the Peters projection if you are more interested in that. But we know that there are a little more than 54 million square miles of land and about 142 million square miles of water. If we take the land area divided by the total area, that will equal the probability. So the land area is a little over 54 million. The total area of the earth is almost 197 million. We do that division and we get a decimal number of 0.275. Well, what does that mean? That means that there's a 27.5% chance that our satellite will crash on land. Now, conversely, that means there's also a 72.5% chance that the satellite will actually crash in the ocean. Because where is it going to crash? It's either going to crash on land or it's going to crash in the ocean, and those two probabilities need to add up to 100%.
Okay, so let's look at how we deal with a continuous uniform distributions. So first I'm going to draw a graph and then we'll talk about the problem that we're going to do. Whenever I draw a graph, I want to make sure that I use a scale, a uniform scale. So my problem is, assume that the weight loss for the first month of a diet program varies between 6 and 12 pounds and is spread evenly over the range of possibilities, so there is a uniform distribution. Find the probability of the given range of pounds lost. So first I need to do the 6 and 12. So let's go ahead and do my uniform. So let's do a uniform scale here. That one isn't. Okay, so if this is 0 pounds, 1, 2, 3, 4, 5 pounds, 6, 7, 8, 9, 10 pounds, and we know that our weight loss is between 6 and 12 pounds. So I'm simply going to put those on my graph, and right now I'm giving them an arbitrary height. And notice when I have a uniform distribution, the shape of the distribution is a rectangle. Now we need to figure out how high our distribution is. Well, because the length of our distribution is 6 pounds, and we know the area is 1, and the area equals length times width, and the area has to be 1. The length is 6, so our width, when we divide both sides by 6, is going to be 1/6. So we know this is 1/6. That's our probability. So we know the height of our rectangle is 1/6. So the first question says more than 11 pounds. So if we want to know what's the probability that our weight loss is more than 11 pounds, we need to find the area of the rectangle between 11 pounds and 12 pounds. Well, we know the width is going to be 1 pound, and our height is 1/6. So since our probability is the same as the area of this rectangle, it's going to be 1 times 1/6, which is 1/6. So the probability that someone will lose more than 11 pounds is going to be 1/6 of the time. Let's look at another one. What's the probability that the weight loss will be less than 11 pounds? Well, we know since the area under the curve is 1, and less than 11 pounds would be down here, then I know that's going to be 6 minus 11, the width, times the height, which is 1/6. Well, 6 minus 11 is 5. 5 times 1/6 is 5/6. Now it makes sense that the probability that's greater than 11 is equal to 1/6, and the probability that is less than 11 is equal to 5/6, because it's kind of like the probability that it will happen, the probability that it won't happen. Now let's look at what happens when we do a between. So what's the probability that our weight loss will be between 10 pounds and 8.5 pounds? So we need to look at a new rectangle. So here's our 10-pound mark. I'm going to mark that on there. And then 9, 8. So 8.5 would be right in between there. So I'm looking for the area of this rectangle right here. So I need to find the distance, and the length is going to be 10 minus 8.5. So that's going to be the length of my rectangle, and then the width is still 1/6. So that's going to be 1.5. I'm going to change it to a fraction. 3/2 times 1/6 comes out to be 1/4. So 1/4 of the time the weight loss will be between 8.5 and 10 pounds. So when you do a uniform distribution, it's just a rectangle. And you will know the width of the rectangle, and you may have to calculate its height. But the key is that the area under the curve is always equal to 1.
So here is, on the slides, a similar problem to what we just finished. We have voltage that varies from 123 to 125 volts, and all volts are equally probable, and we want to know what the probability is that a randomly selected voltage is greater than 124.5 volts. So we're going to find the area. Since the width of our rectangle is 2 volts, then the height has to be 0.5, because remember, the area under the curve is always going to be 1. So since the area now that we're interested in, 124.5 to 125, is 0.5, and the height of our rectangle is 0.5, we can say that there is a 25% chance that a randomly selected voltage will be between 124.5 volts and 125 volts. That leads us back to the standard normal distribution. And what we're going to do here is we're going to look at this, and remember, it's a probability distribution. And the important things is the area is 1, the mean is 0, and the standard deviation, or the width, is 1. And this is going to be a very, very, very important distribution to us, because this is how we're going to translate our probabilities as we go forward in the course. So let's find the probabilities when we're given a z-score. Now there's two ways to do this. This is, we can use table A2 that's in the back of your book, or on the yellow sheet I gave you at the beginning of class. But we're going to focus mostly on using StatCrunch, because it's a tool that makes your lives extremely easy. So here we're going to do, so you can see there are different ways to do it. We are going to focus on StatCrunch. Okay, let's look how to do these types of calculations on StatCrunch. We're going to go to Stat Calculators, and then we're going to go down to Normal. You don't need to have anything in your data table at all. And here we have a standard normal distribution where the mean is 0 and the standard deviation is 1. Let's look at an example that's going to be in a slide or two, where we have the Precision Scientific Instrument Company, and they make thermometers. And the thermometers are supposed to give readings of 0 degrees Celsius at the freezing point of water. And so they've done tests on large samples of these thermometers, and they know that sometimes they give readings that are too low and readings that are too high. And let's assume that the mean reading is 0 and the standard deviation of the readings is 1. So in other words, our mean in this case is 0 degrees and our standard deviation is 1 degree. And we're going to assume that they're normally distributed. If one of the thermometers at random is selected, find the probability that at the freezing point of water the reading is less than 1.27 degrees. So all we're going to do is, there's our mean, there's our standard deviation. We want to know the probability that something will be less than 1.27 degrees. And we hit compute. And what you see is a very nice sketch. Notice that a reading of 1.27 will be 1.27 standard deviation units above the mean. We're looking at the area to the left of that, the area less than. If it was less than 0, it'd be 50%. Our answer is more than 50%. So we can say that 0.8979 is the probability that a thermometer will read 1.27 degrees or less. I would like to see you translate that into percent, like 89.8% of the time a thermometer will read 1.27 degrees at the freezing point of water or less. That helps you understand what it means. I also would like to see you make a sketch like this as you go forward so that you understand the relationship between probability and area.
This is table A2 that you can find in the back of your book. I have a hardcover book, so mine is in the back end pages. If you have a soft cover book, it's going to be in the appendices, or it's on the yellow sheet I gave you. Now, table A2 has two parts. It has positive z-scores and it has negative z-scores, and it shows us the area to the left. So what this table shows us is we have the first page, which are the negative z-scores. So this is going to be the area to the left of the mean. I'm going to go back to that page. Your z-tables here are always your cumulative area from the left. So if you need to find the area greater than, you need to do some manipulation of the table. How do we use the table? Well, it's only for standard normal distribution, which has the mean of 0 and the standard deviation of 1. And so it's on two pages. One page is for negative z-scores, the other for positive. And then it's very, very important to realize that each value in the body is the area from the left. This is very important when you use the table. So we need to be sure that we understand the difference between z-scores and areas. When we look at the table, the z-score is the distance along the horizontal scale.
Now the area is the region under the curve. So if we were really good and we knew calculus, we could calculate the area under the curve using that formula from the first slide of the chapter. But we have table A to help, A2 to help us with that, or StatCrunch. And then we'll look at how to use that table in just a second here. So here's that problem I just did for you on StatCrunch. In this case, our distribution already has the mean of 0 and the standard deviation of 1. And we want to know when the true temperature is 0 degrees Celsius, what's the probability that the thermometer will read less than 1.27 degrees. So here's our sketch. And we've already done this, and you already know that the area is going to be 0.898. Ours was just a little bit different than that when we use StatCrunch because it takes it out to a lot more digits, but it would round to the same thing. Remember, we're going to change when we use the table, we're always going to change our scores to a z-score. That's very important because we have an unlimited number of normal distributions, but we only have one standard normal distribution. And by standardizing it, we make the mean of the distribution 0 and the standard deviation 1. So now my z-score was 1.27. So I'm going to find the 1.2 along the left margin of table A. I'm going to find the last digit along the top line. And then I look to see where those two intersect. And so I can read my probability to the left of that z-score right off of table A, 0.8980. And again, there's our sketch and exactly what we've already seen. So again, the probability of randomly selecting a thermometer with a reading less than 1.27 degrees is about 89.8%. Again, write your answer in a sentence, and I would recommend that you change the decimal to a percent. For me, it's easier to understand. Okay, now we're looking at another one. And again, it's the same scenario, but this time we want to know what's the probability that our thermometers will read above a negative 1.23 degrees. We're going to find that in the table. And what's going to happen here is, as we go forward, we need to adjust the table. Now, on the table, when we look up a negative 1.23, we don't find 0.8907. If we look up a negative 1.23, we find the table number of 0.1093. That is the area to the left. That's the area down here, but that isn't what we're interested in. We're interested in the area above that. So we have to take the total area under the curve, which is 1, minus our table number to get our answer that we're interested in. And this is where your sketch becomes so important. Am I looking to the area to the left or the area to the right? And again, put it in a sentence. The probability of a randomly selected thermometer with a reading above a negative 1.23 is about 89.07%. So let's go back to StatCrunch and let's look at this. How do we figure out the area above? Well, notice that we have an operator here that we can change. So we're going to change that to greater than or equal to, and we are interested in a negative 1.23 degrees. And we simply click compute and we have our answer directly. So there's no looking up a number. Do I have to take it away from 1? Can I read the number right off the table? It does it correctly. And again, about 89% of the time, when the true temperature is 0, our thermometer will read a negative 1.23 degrees or above. Then if we go to the next example, is find the probability that it reads at the freezing point of water between a negative 2 and 1.5 degrees. To do one of those types of problems, you're going to look at it and click the between button. Check that your mean and your standard deviation are still set. You can see I have already done this, and so my lower limit is a negative 2, my upper limit is a positive 1.5. I'm going to click compute and I get 0.9104. So what happens, I can say 91% of the thermometers will read somewhere between a negative 2 degrees Celsius, a positive 1.5 degrees Celsius when the true temperature is 0. Or I can say, if I randomly pick one thermometer, I have a probability of 91% that they will read somewhere between a negative 2 degrees and a positive 1.5 degrees. I will tell you that on the next slides and on pages 275 and 276, they talk about how to do a between calculations, and I highly recommend you use StatCrunch because it is so simple and there are a lot fewer places where you can get confused. So here we have the example that we just did on StatCrunch. What you would need to do is you need to find, if you want to do it on the table, you want to find the total area to the left of 1.5 and subtract the area to the left of a negative 2, and then you would calculate the area in between, and it's the same thing that we got on StatCrunch very easily. And so again, I highly recommend you use StatCrunch for these calculations. And here's the notation. And again, this talks about how to go through the calculations. When we know a probability and we want to find the z-score. So these are inside out calculations if you're using the table. Remember, the z-scores are on the outside margins of the table and the probabilities are in the inside of the table. So what we're going to do is, if we need to find a z-score when we know the probability, we're going to search the body of the table. So we're going to use the cumulative area from the left to locate the closest probability, again in the body of the table, and then we can go out to the edges to identify our corresponding z-score. So let's say I want to find the 95th percentile. Well, the 95th percentile means that 95% of the individuals scored less than that, and so our table number will be 0.5. So what we're going to do, our table number will be 0.95. So what we're going to do is we're going to go to the table, we're going to search in the body of the table, and we're going to find the number that's as close to 0.95 as we can. And it is between 1.64 and 1.65, and so we find the mean between those two, so our z-score is 1.645. Let's say we want to find the bottom 2.5% and the top 2.5%. Well, one of the things we can do is simply look at the bottom, and then we will find a negative z-score. The z-score that is the boundary for the upper 2.5% will just be the opposite sign of that. So again, we're going to look in the table, we're going to look up 0.025 as close as we can, and we come up with a negative 1.96. And so then our other z-score will be a positive 1.96. Let's look at how we're going to do those backwards table A2 calculations. So again, we wanted to know the value of the 95th percentile. So again, what I'm going to do is I'm still dealing with my standard normal curve, so my mean is still 0 and my standard deviation is still 1. And what's going to happen is I need to do a standard, and 95th percentile is below. So I'm going to click the less than or equal to button, and then I'm simply going to do my probability as 0.95. And when I do that, I get 1.6448536, and that rounds to 1.645, just like it would have if we did the table. Now in the next slide, they asked about, well, what about the bottom 2.5% and the top 2.5%? We can do this, and again, I'm going to use the less than, but I'm going to go over here to my probability and do 0.025. And when I do that, I get a negative 1.959, which rounds to 1.96. Now, we round this to 2 decimal places because that's what the table gives us. Now, if you want to double check that the boundary of the boundary that there would be 2.5% above, all you need to do is change that. Let's get rid of that and do 0.025 and do compute, and you can see we get a positive 1.96. So that's how you would do those, knowing the probability or the proportion going back to the z-score. So what we've done in this first section of our lecture is we have talked about density curves, and we talked about relationship between the area and the probability. So remember, the probability of something happening is the area under the curve. We talked both about uniform distributions and normal distributions. We talked about the standard normal distribution, where the mean is 0 and the standard deviation is 1. We looked at how you use table A2, and we looked at how you use StatCrunch to do the same calculations. So that's the end of the lecture on 6.1 and 6.2.